Hi, today we're looking at 8.3 geometric sequence and series. We have talked about arithmetic so far, and we've talked about different kinds of sequences that don't have specific patterns. Today we're looking at the specific pattern of geometric. So the definition of a geometric sequence is its consecutive terms of the sequence. In other words, it's still a sequence, it's still separated by a comma, but the consecutive terms have a common ratio instead of a common difference. So instead of saying they have a common D, we're going to say they have a common R. So if this is my sequence right here, to find that common ratio, I would take a sub 2 divided by a sub 1, a sub 3 divided by a sub 2, always the term further down in the sequence divided by the one that precedes it. And that's all should be the same, and that's what our common ratio is. And of course, the ratio is not going to be 0. So the model for the geometric sequence is a sub n, that's the nth model, right? Nth term model, and we have a sub 1, which is our beginning term, and then we have r to the n minus 1. So this is the model that we would use anytime we're talking about working with a geometric sequence. So here's the first one, and it says a sub 1 is 3, so that's our first term. R is 2, so they're actually just telling you right up front that it is a geometric sequence because they're giving you an R value. And it wants us to write the first 5 terms of the geometric sequence. So seeing this is the first one that we've done, I worked through each step and worked it out. But I would not expect you to do that because I know that you can do a lot of this calculation in your head. But let's just kind of go through one time where we're doing all of it. So a sub 1 would be the first term, and so to find the second term, I'm going to do the first term times the ratio of 2, which they gave us, and then it's going to be 2 minus 1 because our n is 2, so this is 2 minus 1. So now I have 2 to the first power. Well, 2 to the first power is just 2, so 3 times 2 gives me 6. So our first term is a sub 1 is 3, our second term a sub 2 is 6. So then to calculate the third term, it's the first term times the common ratio that they gave us of 2. My n value is 3, so I'm going to do 3 minus 1, which is 2. So 2 to the second power is 4. 3 times 4 gives me my value of a sub 3 being 12. So to find 4, it's the third terms times the common ratio of 2, which they gave us. The n is 4, so I'm going to say 4 minus 1, which is 3. Then 2 to the third power is 8 times the 3, which was the first term, and 8 times 3 is 24. So now we have 4 of our terms. So when we go to calculate the fifth and final term, we have the first term times the common ratio of 2. The n value is 5, so 5 minus 1 is 4. 2 to the fourth power is 16. 3 times 16 is 48. So if I'm listing it out because it wants us to write the first 5 terms, I would say 3, 6, 12, 24, 48. Remember, this first value is a sub 1, and it moves up through to a sub 5. You should always start with a sub 1 unless you're told to do something different. So that's kind of the general process, walking through it. I would not expect to see all of this computation on any kind of assessment for me, but I always felt like it's a good thing to start with one worked out, just so there's no misconceptions as we move on to the rest of the questions. So the next one, we're doing problem 2. They're giving us an a sub 1 value of 20, which means they're giving us the first term. They're giving us a ratio of 1.05. And then they're saying find the 15th term. And we're not going to just list this out and calculate 15 times. And I don't want to see a list of just 15 numbers added together. What we're doing and learning how to do is to work with the model. So that's what I want to see as your work and your supporting work. Okay, so it's geometric, so that's the model that we're using. And remember, these are a lot of the same patterns and processes we learned from arithmetic. We're just using a different sequence. So my a sub 1 is 20, and that's going to go right here. I'm finding the 15th term, so I'm finding a sub 15, so be sure you're using good strong notation, times the ratio here would be 1.05, and then we're finding the 15th term, or 15 minus 1, which would be 14. So this is actually what we're calculating once we get all that information plugged in. So I would do 1.04 to the 14th power times 20, which gives us approximately 39.599. So be sure that when you're using your calculator, you're paying attention to how it's rounded, all of those kind of things. So like we'll do one where I'll go ahead and put it in, so I think you can see right there. So I would say 20 parenthesis 1 plus 0.05, or 1.05, excuse me, to the 14th power. And that gives me that full decimal there, and because we're in pre-AP, advanced Pre-cal, excuse me, I still slip on that just a bit. Advanced pre-cal, we're going to always remember 3 decimal places because we're just going to be in such good habits by the time we roll into our calculus class that we're not going to have to think about what place to round to. 3 places unless they tell you otherwise, or we're talking about money. All right, so moving on to question 3. You are given a partial sequence here, 5, 15, 45, because it's separated by commas, dot, dot, dot means goes on forever. We're going to find the 12th term. So again, we're not going to try and list out and count up and do things like that to get to 12. We're going to use the models. So what model is this? Well, I can see that I have a 1, a sub 1, so I know that. And is it a ratio? Do I know what the ratio is? Well, I'm really not given that, but I do know that I'm finding the 12th term, so that would be 12 minus 1. So then I'm going to put in my 5 for A, and you could have done that all in one step. Well, how do I figure out the ratio? It's not given here, but it kind of is given because it's a list of consecutive values, right? And so if I do 15 minus 5, that's definitely not the same thing as 45 minus 15. But if I do 15 divided by 5 and 45 divided by 15, I do get that common ratio of 3. So when you have a consecutive list like that, it's super easy to find the common ratio. So now that I know that the common ratio here would be 3, then I'm going to plug it into my model that we talked about. I'm going to put in my first value. I know 12 minus 1 is 11, so 3 to the 11th times 5 gives me 885,735. Okay, so this is one where it's looking from a list. How do you use that geometric model once you've determined it is geometric? All right, so now we're on 4. So a sub 4 is 125. A sub 10 is 125 over 64. And we want to find the 14th term. So the model work that we're using should use 10 and 4. And then we are finding the 14th term. Okay? So, all of this is on here. All right. So as I'm working through this, I would say, well, I'm going to end with 10, which is this one. And I'm going to start with 4, which is this one. And how many common ratios are there between 10 and 4? That's what 6 is. Remember, we just count this up. We're not trying to worry about the model when we can count and figure the number of differences in between. So then I plug in my given information. So a sub 10 is 125 over 64. A sub 4 is 125 times r to the 6th. So in other words, to get r to the 6th by itself, so I can get down to this r, which is kind of hidden inside the exponent, I'm going to divide both sides by 125 or multiply by 1 over 125. And when I multiply this by 1 over 125, the 125s are going to cancel. And I'm just left with 1/6. All right, how do I get down to this r? If it's the power of 6, I want to take the 6th root. So the 6th root is what times itself? 6 times gives me 1, and that's 1. And then what times itself? 6 times gives me 64. And you should recognize that's in 2. Remember the list of patterns that I gave you from day 1? That's on that list, and you need to know those numbers. So remember that when you're taking the radical of a fraction, you can just take the radical of the top and the radical of the bottom, and that's all I did right here. So once I know what my r is, then I can go to my model. But notice I started at a sub 10. When we did arithmetic, we tended to start with a smaller number. Here I'm actually picking the bigger number because there's fewer ratios between 10 and 14 than there is between 4 and 14, which means the power here that I'm working with would be a tad bit smaller if I can look at 4 common ratios, you know, as a part to what I would have to find the 10 common ratios between 4 and 14. So then I replace what I know, and I have my ratio that we just calculated. And so 1/2 to the 4th power is 1/16. 125 over 64 is just 125 over 64. Nothing here simplifies. 125 won't simplify with 16. 125 won't simplify with 64. So multiply the tops, then you multiply the bottoms, and you get a sub 14 is 125 over 1024. And remember, this is the 14th number in this sequence, right? It's the 14th position. So pay close attention to, are you doing a number or are you doing a sum? All right, in this example, we are given a beginning term, we are given a ratio, and we're given n. So what I want to find is find the nth term. So what's that answer going to look like? Well, if you said a model, then we need to explore just a little bit closer. So you fell into my trap because that was a trap. Because it does say find the nth term, but what is it giving me right here? it's giving me term 10. So it's no longer the nth term, it's actually a sub 10. So pay real attention when you're looking at a problem. How they give you that information definitely influences how you go about solving the problem. So then I go to my geometric model. I know it's geometric because they give me the common ratio. I am going to find a sub 10. I'm going to begin with a sub 1, and then that's going to be r to the 10 minus 1, or 9 common differences. So we have a sub 1 is 4, 1/2 to the 9th power. I can calculate that out. 1/2 to the 9th power is 1 over 512 because it's 1 to the 9th, 2 to the 9th. And then 4 and 12 are going to simplify to 1 over 128. So that's my a sub n term. Okay, so you're taking a lot of stuff that you know, we're putting it all together in these problems. All right, 6. A sub 1 is 16, a sub 4 is 27 over 4. And we're trying to find a sub 3. So we're finding a term that's in between these two. What don't I know? Well, you're right, I don't know the common ratio, but I can find it. And so what I'm going to do to find it is I'm going to use my models in this case. So I'm going to start with a sub 1, I'm going to go to a sub 4, that's 3 common ratios, and then to get rid of the 16, I multiply by 1 over 16, and then simplify it. So I get 27 over 64 is what r cubed equals. Now to get down to the r that's contained inside the exponent, I'm going to take the third root of both sides. So the third root of r cubed is just r. The third root of this fraction means I'm taking the third root of the top and the third root over the bottom. So the third root of 27 is 3, and the third root of 64 is 4. So here's my ratio. Okay? So then over here I have a sub 3 equals 16 times 3/4 to the 2. And when I get 3/4 to the 2, that's just multiplying the fraction together. So 3 times 3 is 9, 4 times 4 is 16. So we can see right here then, 16s are in common. They're on that diagonal. They're going to cancel, and I'm left with 9. And that's the value of a sub 3. So hopefully you're feeling comfortable working with a geometric model. Now let's look at geometric series notations, because we need to be able to add things up with geometric series just like we add things up with arithmetic series. So remember that if it's a sequence, it's a list, an ordered list separated by a comma. If it's a series, then it's an ordered list, but it's separated by plus and minus signs because you're going to be adding all of the terms together. So this is a little different in geometric than arithmetic because a geometric has two different kinds of summation models, whereas in arithmetic you have two models to accomplish the same task. So the first one we're going to look at is finite. And when we're finding the sum of a finite series, we're saying we know what the ending value is, and so we're adding up between those two places. So there's actually two ways you can write that model. You can put the a sub 1 in the numerator, or you can bring the a sub 1 in front of the entire fraction, because we learned a long time ago when we multiply fractions, we multiply the tops, then we multiply the bottoms. And so when we do that, that would be like saying a sub 1 over 1, so I'd multiply to the top and I'd multiply 1 to the bottom. I don't really have a preference which way you like to think of it. I tend to go this way because this makes my fraction work a little easier, and then I can just multiply it by that a value at the end, but that's totally up to you. So when we're looking at a series, remember a series for geometric would be like a sub 1, that would be a sub 1 times the first ratio, and then a sub 1 times the ratio twice, and then a sub 1 times the ratio 3 times, and then a sub 1 times the ratio 4 times, all the way to the nth model, which would be a sub 1 times n to the r to the n minus 1. And remember, common ratio has to not be equal to 1. Okay, so if you are looking for sigma notation, so this is the sequence model notation, and that's what you're using unless a question specifically says use sigma notation. But if you're using sigma notation, then this is what it looks like. So here is the geometric model. It's going to go from a lower bound of 1 to an upper bound of n, and we would be adding all of those terms together. We could apply the property, that because we know a sub 1 is a number, so we could apply the property and bring a sub 1 out in front, then do our summation and multiply it by a sub 1 in the end. But again, difference in geometric, like a sigma notation, and geometric sequence model notation. Okay, so now we're talking about the sum of an infinite geometric series. So in this case, we don't know where the end is. It's not in sight. We don't know what we're adding to. We're just adding forever, like Buzz Lightyear says, to infinity and beyond. So when we're doing something and summing geometric to forever, then the model is actually a little different. So we have a different model. There is a condition here that must be met in order to use that model. And that condition is that the ratio, the absolute value of the ratio, has to be less than 1. So what that means in terms of numbers, if the biggest number you can get is 1, right, because I could do -1 and it gets +1, and I could do +1 and it gets +1, that means the values that are okay to use are those values that fall between -1, not including 0, because we already defined that the ratio can't be 0, all the way up to +1. So -1 to 0, 0 to 1, not including 0. If the condition has been met, then you can go to your model, which is just the sum, notice no subscript, of a sub 1 over 1 minus r. Okay, you could also write it by pulling the a sub 1 off the front, just like we did in the finite, but notice no subscripts here, because subscripts don't, subscripts tell us we have a place to add to, and this summation does not. So again, the ratio is going to look the same, so there's not much that changes there. But there are 3 models. So if we're doing sigma, notice that the upper bound on sigma is to infinity. And remember, we can't plug infinity into the calculator. So we would have to explore a little bit further. And that is sigma notation just in general. We could use the property that we learned that says if a sub 1 is a number, which it is, you can pull that out in front of the sigma notation and try and work with that. So you can kind of try and figure out what is this converging toward, and then you can multiply it by that a value at the end. Or you can do the model work, which is the sequence model here, which is a sub 1 over 1 minus r. So don't use sigma unless you're told to use sigma. Work with the models. That's the whole point of what we're learning here and becoming proficient at, is knowing how to use which model, when to use each model, and what you need to be able to use the different models. All right, so we have a 3-step process for infinite sums of a geometric sequence. So the first thing is we have to establish the condition to use the model. That means in my work, step 1, I should state what the ratio is, and is the absolute value less than 1. If the absolute value of r isn't less than 1, then we'll explore further. So once I establish that it is less than 1, then the next thing I'm going to see in your work is where you calculate what a sub 1 is. Sometimes it's not always just the first number right here. Depending on my lower bound, that can change. So the second thing in your work must always be stating what a sub 1 is. Okay? Then finally, if you've met the condition and you've stated what a sub 1 is, then you can just go to your model and apply your model, putting in all the information that you have. Okay? If the absolute value of 1 is greater than 1, then we need to explore further. So the most common one we see is when the absolute value of the r is positive and bigger than 1. When it's positive and bigger than 1, then each term in the sequence is getting larger, so the sequence moves toward positive infinity. So look at the model back up here for a second. If r is bigger than 1, then each of these powers are getting bigger and bigger, right? So then multiplying by a ratio of r squared is going to be a bigger number. Well, then when we multiply by a ratio of r to the third, that's going to be an even bigger number. And r to the fourth would be an even bigger number. So we just keep multiplying by bigger and bigger numbers, which means that value just keeps getting bigger and bigger, and that's why it's moving toward positive infinity. So that's one thing to watch out for. The second thing that we would explore further for would be if the r value is negative but greater than 1. If it's negative but greater than 1, then the value can't be determined. So we would say, you could just say can't be determined. That's probably the easiest way. And so the value of each term in this case, so here's my example so you can see what I'm talking about. So if n is 1, I put 1 in here, I get negative 3/2. If n is 2 and I put it in here, I get positive 9/4. If n is 3 and I put it in here, I get negative 27/8. And then if n is 4 and I put it in here, I get positive 81/16. And if n is 5 and I put it in here, I get negative 243/52. So can you see that we're kind of bouncing back and forth? We're subtracting a bigger negative number and then a smaller, and adding a positive number and a negative number and a positive number. So it's never actually going to converge. It's just going to kind of not necessarily oscillate, because it's not going to the same high and the same low every time, but it is bouncing back and forth, which means we can't actually determine a number. So those are the two cases that we explore further when the absolute value of the ratio is bigger than 1. So remember we said that's the first thing we establish the condition for? That's why. Because if this is this case and you're trying to calculate a number, then you're actually trying to calculate a number that doesn't really exist, because it would be going to infinity or it wouldn't be settling out to anything. And so you can waste a whole lot of time. Okay, so we're just going to kind of work through, and I worked out 7 so you could see what we've done in the past and what working through the model is going to be, and then we'll work through a few more together. So this is the problem. Our lower bound is 1, our upper bound is 12. Here is the geometric model, and we want to find the 12th term. So the first thing I would do is take a minute and say, what type is it? Well, it's going to 12, so it's a finite. Why is that important? Because we have two different models, and we want to make sure that we're using the model that represents partial sum, the S sub n model. So that's where I would start. And then if you're doing model work, you're going to jump down here and you're going to plug in what you know. Well, I know I'm calculating to the sum to 12. I know a sub 1 is 16 because I put the 1 in here, and 1 minus 1 is 0. 1/2 to the 0 is 1. 1 times 16 is 16. So we would have established the ratio, we would have calculated the a value, and then we would plug everything in. So when I calculate this out, I get a sum of 4,095 to 128. Well, if we did it before what we're looking at today with the models, then we would have pulled the 16 out in front, and we would have calculated some values, and then we would have tried to see what those are going to add up to, which was 4,095 over 2,048. Then we would have multiplied it by 16, and then we would have got our answer. Working with the model was way quicker and a lot less cumbersome. So now we're going to work through a few problems, and then I will let you go so you can start working on the daily practice. All right, so let's look at question 8. So we're giving information in sigma notation, and we're asked to find S sub 100. So I'm asked to find the sum of the first 100 terms. So the first thing I look right here and I go, okay, I've got a bound, so this is finite. So the first thing I always do is answer the question. What type is it? It's finite. What's the model? Here. And that way I just don't, I give myself a chance to not get confused along in the work, and I know exactly where I'm starting from. And then if I know exactly where I'm starting from, I know exactly what I need to go calculate or figure out to be able to do that. So I said, okay, what do I have? I have a ratio of 2/3. I have an A1 value. The lower bound is 1, so 1 minus 1 is 0. 2/3 to the 0 power is 1 times 15 means I have an A sub 1 value of 15. And then if I'm going from 1 to 100, 100 minus 1 is 99 plus 1 gives me an n value of 100. So now once I know these three things, I can just go straight to my model. I'm finding S sub 100. Be sure you're using good notation, because now we could be summing to infinity or we could be summing to a value. Then I have an A sub 1, so I'm doing the model where the A sub 1 is in front. And I do 1 minus 2/3 to the 100 over 1 minus 2/3. And so when I evaluate this part of my fraction, I get 3 times 15, which gives me an S sub 100 of 45. Remember, no math magic numbers. If you're writing something down here, you need to state what it is. So I need to see S sub 100 equals 45. Number 9. So notice the summation goes from 0 to 1 to infinity. So how is this problem different from number 8? Well, that's it right there. That is to infinity, not to a number. So there's no upper bound, which means we are looking at the type to be infinite and the model to be S equals A sub 1 over 1 minus R. Now remember, when we use this model, the absolute value of R has to be less than 1. So those kind of go together. You can't have one without the other. So that means my model, the work for a problem like this that's finite, is that 3 steps we talked about. We're going to establish the condition by identifying that the absolute value of R is less than 1. We're going to find A sub 1, and then we're going to move on to using the model. Okay? So here we go. So the first thing I'm doing is establishing my condition. So I said the ratio equals -1/2. The absolute value of -1/2 is less than 1. Check, I've established my condition. Now I'm going to determine what A sub 1 is. So I take the lower bound, which is 0. I replace n in my model with 0, and -1/2 to the 0 power is 1. So A sub 1 is 1. Okay? Then I'm going to go to my model, which is S with no subscript, equals 1 over 1 plus 1/2. So a common denominator down here means I'm going to have 2 over 2 plus 1 over 2, which is 3 over 2. And when I'm dividing by a fraction, that's the same thing as multiplying by that fraction. And so 1 times 2/3 just means that this is going to sum to the value 2/3. So what this is saying is since the absolute value of -1 is less than 1, then the sequence converges to the value of 2/3. So it's converging to a numerical value. All right, so here's question 10. So immediately I should jump out and see, okay, that's to infinity, which means I am doing an infinite sum. So if it's an infinite sum, I'm going to use that model, and I'm going to remember that the absolute value of r has to be less than 1. Okay, again, they go together, right? So then when we work through the problem, we're going to have to establish our condition first. So the ratio is 1/3, so that's r equals 1/3, so the absolute value of 1/3 is less than 1. Then I have to find my a sub 1, so the lower bound is 1, so I put the 1 in right there, and I have 1/3 to the first power is 1/3. 1/3 times 15 is 15 over 3, or 5. Now I am kind of thinking ahead of time because I know I'm going to have to use the fraction 1/3 in my work, and I know this is 15/3. So I'm going to go ahead and work through the rest of the problem with 15/3. It's perfectly acceptable for you to work through the rest of the problem with 5. Okay, so now I've established my condition, I've calculated my a sub 1, so now I can go to my model. So I did 15 over 3, or you could put 5, and 1 minus 1/3 on the bottom. So when I'm combining the bottom, changing a whole number to 3 over 3 means 3 minus 1 is 2/3. When I'm dividing by a fraction, I multiply by the reciprocal. So I have 15/3 times 3/2. The 3's are going to go away, and that leaves me with a sum of 15/2. So that's what the number, or that's what the value when you make the summation is converging toward, is 15/2. Okay, so again, since absolute value of 1/3 is less than 1, the sequence converges to the value of 15/2. All right, last one, number 11. So I'm looking at the problem and I'm going, whoops, 1 to infinity, which means it's infinite. So that's my type, which means I'm going to use this model, and I'm going to always remember that the absolute value has to be less than 1. So I have to establish my condition, find my A1 value, and then use the model. Okay, so we're going to go down here to the first part. So step 1 is establishing the condition. So my ratio is 3/2. Absolute value of 3/2 is greater than 1. It's not less than 1, which means it's not converging to a value. So we need to explore further. So since it's not converging to a value, then I want to look and see what it's doing. Since this is positive and bigger than 1, remember each time you multiply by a new ratio, you're going to be multiplying by a bigger number, and you are just going to be blowing that value up because you're just going to be multiplying by bigger and bigger and bigger numbers. So that means that the series will approach positive infinity. Okay? So since we established the condition that wasn't possible in step 1, then we explore further to figure out exactly what's going on. And that's the last one in today's notes. So you have some daily practice to work on. Please come ready with your questions next time. Next time we are going to move into our last section, 8.4, which is binomial expansion and Pascal's triangle. Have a great evening. Bye.